Log on, tune in, find out. Another good idea from Cambridge.
To welcome Bill Lionheart to give our seminar, and he's going to talk on, or at least the title is Photoelastic Tomography.
Thank you. And this is joint work with Vladimir Shafutinov and David Shotton, who is my student. And I've name-checked the Photon Science Institute because they've actually given me some laboratory space to try this experimentally. So that's the least I owe them. So, photoelastic tomography, and as you saw, I just changed the title from a previous talk, which was something like tensor tomography, because I am actually doing tomography of tensor fields. So the talk will go so far. I'll say how it comes from Maxwell's equations, because underlying it, it is an inverse problem for anisotropic Maxwells. I'm going to tell you about the TTRT, the truncated transverse ray transform, and an explicit inversion formula for that Shafutinov and I did, and then some stability results that are largely down to David Shotton, and also some numerics. We don't have this, we have only simulated data, we don't yet have real data that's good enough. Okay, so photoelastic tomography in a nutshell.
So, do you have the microphone on?
Thank you. It's on, but not on.
Can you just hang on a second while we check that your words will be immortalised? Is it right now? Yeah. Okay, thanks.
Okay, so for the purposes of anyone else out there in cyberspace listening, I'll just briefly repeat that I'm going to talk about photoelastic tomography, and we'll say how this comes from elasticity and Maxwell's equations. I'm going to talk about inverting the truncated transverse ray transform, its stability, and some numerical results. Okay, so a quick summary. I'm hoping to give this talk on several levels, right? So some of you might have seen some of this work before, in which case you might actually be interested in some of the fiddly details, and some of you might sort of doze off through parts of it and then wake up again at the end when you see the results. And that's all fine. Hopefully it will... you'll be able to listen to it on various levels. But here's a kind of overview, a summary. First of all, the permittivity tensor, the dielectric permittivity, is linearly related to the stress tensor field. So, of course, the point is that we're going to measure something with light to infer something about stress, so that's a necessary thing. Permittivity tensors that are close to a constant times Dirac delta Ij propagate in straight lines approximately. So in other words, although it's anisotropic, if it's nearly isotropic, then pretty much the light goes in straight lines still. It's not a big enough change to mess that up. But the polarization state of light is changed in a way that depends on the projection of the permittivity tensor normal to a ray. So, so this works in a certain range where some approximations hold. In particular, the linear approximations to this, which requires a small stress, is the transverse ray transform, the integral of the projection of a tensor onto rays. And that's actually quite easy to invert, but unfortunately, it's very hard to measure phase changes of light going through large objects. And so we don't know that transverse ray transform. We only know something called the truncated transverse ray transform, which makes it all a lot more complicated. So our aim is to explicitly invert the truncated transverse ray transform on trace-free symmetric rank 2 tensors, so those will be our permittivity tensors, and also with as small a data set as we can. And when you see what the apparatus looks like, you'll understand that a little bit. Okay, so a little bit about photoelasticity, which is a very old subject. Here is a cross-section through a thread on a nut and a bolt, viewed through polarizing filters in white light. And what you can see is the stress concentrations resulting in fringes. In particular, the more the load is carried on these threads, the bigger the more fringes we have here. In fact, it also illustrates something perhaps quite alarming, that when you tighten a nut on a bolt, most of the load is taken on the first few threads, because the rest of the threads deform. Let me do it like this. There's the threads. As you tighten it, some of them don't touch anymore. Woe betide anyone who used a finite element model, assuming they were all touching, and calculated maximum stress. It's still very worthwhile to make physical models with a transparent material and measure the stress to make sure that you have actually got your assumptions right. We do experiments more like this with monochromatic light, and here is a block of epoxy supported on some blocks, and it had pretty much a point load there. And we can see these stress patterns. So roughly, and you can see what you want to do. If you actually look at this in real life, you can see that these are three-dimensional patterns of fringes. And so our idea is to tomographically find the stress by looking at it from all directions. The actual point of this is that the traditional way, you physically slice the object with a saw. I mean, there's no possibility to go back and say, if only I tightened it a few more turns, you know? It takes days to do this. So if we can do it without destroying the sample, then we can do these experiments much more quickly. And of course you get more data in 3D than just a plane. Okay, stress optic law. So sigma is going to be the stress. This kind of epsilon is going to be the permittivity, which of course is confusing because it might also be strain. That will be the other epsilon. But the point is that the permittivity would be isotropic if there's no stress. So that's kind of background permittivity. And then it's got two constants depending on the stress. This is the trace of the stress times the identity. And this is the rest of it. In fact, you can separate it into part depending on the trace and part depending on the trace-free part. And the trace-free part there is called deviatoric stress. But actually, this is a little bit of representation theory of groups. Any tensor that's invariant under an SO3 action must be any linear map between symmetric tensor field that is invariant under SO3 action must actually be split into just scalar multiples of these two subspaces. Okay, so representation theory. But it's sort of traditional tensor to know that. So there can only be two constants. It depends on the bulk, stress, and the deviatoric part. Fortunately, it's a deviatoric part that breaks stuff, especially metals. So it's not squashing it uniformly that breaks stuff. It's the other part, the deviatoric. So we're more interested in deviatoric, remember that. Okay, so roughly you have light going through the material. The light is polarized by going through a polarization filter, so the waves are only vibrating one direction. And then it goes through some sample. These are changed, and then you put it through another polarizing filter. You can visualize that roughly. It's hard to visualize polarized light. Okay, so it does come from Maxwell's equations. Epsilon here is a tensor. Mu is assumed to be, well, just homogeneous. And we're interested in a perturbation of the permittivity at some background level, which presumably is homogeneous as well, plus something called F, and it's F we're going to look for. Quasi-isotropic means that the anisotropic part, the deviatoric part of f, and its derivatives are small, basically. And this allows us to approximate Maxwell's equations by an ODE along rays. So T is the distance along a ray, E is the electric field, and you can replace Maxwell's equations by an ODE for the E field along a ray. Now, if the permittivity varied too much, actually rays would split and actually you'd lose the ray approximation. But as long as the anisotropy and the difference to isotropic is small, and so it's derivative, then we have this Virchow law, where P is the projection perpendicular to the direction of the ray of this vector. Okay, so we have an ODE along a ray. We have a further approximation to make, because that would be a non-linear inverse problem for epsilon. Okay. So a Born-Neumann series argument, again assuming even smaller permittivity changes, says that the data, which is the solution operator for this ODE, this initial to final data problem, would be the data here T, that the difference in the initial to final data operator can be written as an integral along rays of the projection of the tensor onto the plane perpendicular to the direction of the ray. And so that's the transverse ray transform. It projects perpendicularly, and we'll write that as J of F. So J of F is a transverse ray transform. And it's actually quite a simple and natural thing to do to a tensor field. You just project it perpendicular to the ray. There's roughly three things that you could do with a tensor field and rays that would make sense. Project it in the direction, project it perpendicular direction, and just not project it and integrate it, right? And so this is one of the obvious things to do. And it turns out that if you consider planes normal to a given vector, eta, then the eta component of f can be obtained as exactly an X-ray transform in the plane. So actually that means this one's very easy to invert, because it means you can get all the diagonal components just by measuring on a plane, on planes, parallel planes perpendicular to the diagonal you want. And of course, even though you want off-diagonal terms, as soon as you do non-orthogonal planes, you have all the off-diagonal terms anyway, right? So you can see that that would be very easy to invert, and you'd only need 6 directions. What that means is that you could get your object, rotate it, measure everything, and then just move it through 90 degrees, and then say through 45 degrees, and at each position you just rotate it. And then you get 6 sets of data, and you could easily do it. So, I mean, I'm skipping over this because we can't do that. It's very nice mathematically, but that requires measurement of phase data. Let me just say how that would work in practice, though. Parallel rays of light come in, perhaps with a laser and some lenses. Here's our object, and here's a turntable. This is a transparent tank with some fluid with the same refractive index, so as the sample. So the rays would, if it wasn't stressed, just go straight through, and then the camera is arranged so it measures parallel light as well. This rotates, and we get a full set of X-ray transform data. And then the idea is, if we want to rotate about a different axis, we tilt the block and then rotate. Easier than tilting the laboratory to tilt the object. Okay. And this is Rachel Tomlinson's apparatus. Actually, I've now rebuilt this in the Photon Sciences Institute. I've completely changed the optics, but roughly has a laser, a lens, so that I have parallel light going through here, a camera that measures parallel rays, a matching fluid tank, a polarizer and analyzer that are motorized, and then it's all computer controlled. So that's roughly how it looks. Unfortunately, we can't measure this transverse ray transform because we need to measure phase changes in light that are just too subtle to be able to measure accurately in this context. So what we can measure is called the truncated transverse ray transform. So I need to talk about a different type of projection instead of P, and it's a little bit more complicated. It's called Q, and it's the orthogonal projection onto the subspace of trace-free tensors F. So it's perpendicular to the ray and trace-free. And actually the easiest way to think of it is just to do it with the standard basis vectors and take xi to be the z direction, in which case it's just this. In other words, we've projected away the z components, and then if you see, we've made a trace 0 as well. That's all it does. So you just rotate this, you know what I mean by Q. It projects perpendicular to that ray and then takes away the trace. So you can guess what I'm going to say, that we're going to integrate that thing. And of course that can't see traces of anything. It can't see the hydrostatic stress. It can't see the trace of a matrix. It can only see the deviatoric part. But that's okay, because it's the deviatoric part that breaks stuff. So what we do is we get this projection in integrated, and that's what we can measure. It's a whole lot more complicated. It's got a null space of any multiple of the identity matrix, but that's okay. So we want to invert this. So what was known about this already? Well, Sharafuddinov's book contains an explicit inversion formula for K. So this is quite old, but it assumes we know all rays. Just think about that for a moment. How are you going to achieve that? All rays, right? So I can rotate the object and get all the rays parallel to some plane. And then I have to, so I can do that in 1 degree steps. I mean, that's fine. But then I'm going to have to rotate it through 1 degree steps and do the whole 1 degree rotation around as well. It's just completely unfeasible to do that. And then it's also clearly overdetermined. It's more data than you need. So there's a group in Estonia that does this in practice, mainly for the glass industry, glass components, and in fact beverage glasses. They sell apparatus to more or less do this. But they assume that the stress tensor, its divergence, in other words, differentiate with respect to j and then sum over j is 0. So it's a constraint. So and that's okay for them because their particular origin of their stresses means that's true, that their thermal stresses in the glass. And it's no use for things that are loaded on the boundary, engineering applications. So they have a special reconstruction for this, and they get it to work experimentally. So what we did when we started with this is we just, I think we heard this mentioned in the context of emission computed tomography. You can just write down the matrix and solve it, right? It's just a big linear system. Write down the matrix and solve it. So we did that, and we did numerical inversion, raised parallel to 6 planes. Numerical evidence suggests that less than 6 planes would do. And the thing to remember, and you'll see this a little bit more, is actually for each ray, you measure more than one number. You measure 2 numbers per ray, actually, that are independent. You're measuring a polarization state of an E field. It really has 2 numbers in it. So, okay, so you can guess then that 1 axis would not be enough and 6 would be plenty, but how many would actually do? Okay. So the first general results were reported here, and there's some kind of stability. And in this talk, we'll actually express the stability in terms of Sobolev norms. Okay, so uniqueness for 3 axes. Here's the theorem. A trace-free tensor field is uniquely determined by the data from lines parallel to 3 planes. So take three independent vectors, eta 1, eta 2, eta 3. L eta is the space of rays perpendicular to that vector, and then measure the data for k perpendicular to those rays. Corresponds to doing our experiment with the object tilted relative to the rotation axis in 3 different places. So it turns out that there is an explicit reconstruction, but it's unstable. We'll look at that in more detail. And then for 6 vectors, you could do other cases, but we chose explicitly the unit vectors and then plus or minus them, in other words, the 45-degree directions between them. And it turns out if you take these 6 directions, then the data uniquely determines a trace-free tensor field with a stable explicit reconstruction formula. And you mean you can do it for other choices, it's just more complicated algebra. Okay, so at this point it gets complicated, and there will be a level of complexity here that will be quite hard to follow, but that's the nature of tensor tomography. There's a lot of complicated relations. But let me just sort of give you an overview. We're going to deal with the Fourier transform of f hat. So it's a tensor function of 3 variables, and we just Fourier transform it. And the Fourier frequency variable is going to be called y. And then for each of our rotation axes, for planes, the normal to the planes, we'll actually measure 2 scalar pieces of data whose Fourier transforms we'll call lambda and mu. And I just want you to remember that there are 2 things per ray, and then we've taken the Fourier transform. So what we end up with is a system for the Fourier transform of f, which consists of 2 equations for each axis, system of linear equations. And the rest is just that we can do this in a complicated, explicit way, right? We can do the algebra. But in the end, you could sort of just do it numerically. The question is, how many of these etas do we need? Somewhere between 2 and 6, obviously. Okay, so we've seen already the truncated transverse array transform K, the transverse ray transform, which is just the ordinary projection one, and I did mention there are other ones. The other interesting one is the lateral ray transform, and actually that's just almost the natural one that you do with a vector or a tensor. So if f was a vector field, you just take the dot product with the direction and integrate that. That's the only thing you could think to do, really. And if it's a tensor field, you dot product it on either side. So you contract. A kth order tensor field you contract with k vectors in the direction you are going. So, I mean, this transform arises in other types of, this one, for example, in Doppler acoustic tomography. So this I results in a scalar per ray. And actually there's an inversion formula for those. Up to its null space. We'll denote I eta s on the plane, which is the plane perpendicular to eta plus s times eta, which is just a way of parameterizing parallel planes. So
what do you use the same notation for those 2?
Oh, f could be a vector or a tensor.
No, but you denote the same, both of them denote by if, yes?
Yeah, if actually acts on the direct sum of all symmetric tensor fields.
These are 2 such cases.
Yeah. So these are just 2 cases, but there's an algebra of symmetric tensors, which almost mirrors the algebra of skew-symmetric tensors. There are differential operators between them and so on. It's a complex on which these are defined. So this is part of a bigger story, but we only need these 2 cases. Okay, so the projections P and Q are related. Q is the one that removes the trace, P is the one that just projects perpendicularly, and they differ by this term. And that's important to us. Here, epsilon ij in the direction xi is just delta minus the outer product of those two vectors. So actually that's the projection of the identity perpendicular to that space. Now K, that's our truncated transverse ray transform, can be written as J, the transverse ray transform, plus something that involves the lateral ray transform. And of course, you can guess it's something nice because we do know how to invert these two. So for any eta in the sphere, any unit vector orthogonal to psi, so you've got this direction and you have any vector perpendicular to it, this thing times eta, this is an eigenvector of epsilon. And okay, so let me just see what I can extract from this. That's kf of eta. That's kf of eta dotted with something perpendicular to xi and eta, and that's kf of eta in the eta direction. So I mean that's really an off-diagonal term, and that's a diagonal term. If you think of this as a matrix, that's perpendicular to that. So that's an off-diagonal term, and that's a diagonal term. So there are these two pieces of data that we could get if we knew kf, and we treat those two things separately. In fact, those are the two pieces of data per ray that we want, and we call them K1 and K2 because those are the two pieces of data we measure. In practical systems, this is what actually comes out of your system. So K1 is the off-diagonal term, that's normal to that, and K2 is the diagonal term. And the crucial lemma is that these things that you can measure can be reduced to a lateral ray transform on two-dimensional planes. So that's all you need to take away from that. Those are the two things you measure. We can write them in terms of eyes on two-dimensional planes. Okay, so how does this help? Okay, so I mean we're still in the depth of the rather complicated bit. So and I noticed no one has gone to sleep yet. I gave a similar talk in Oxford and one person fell asleep. I count that as a success. Right, so this relates the K1 and 2, which we measured plane by plane, to lateral ray transform. And so we need to invert the lateral ray transform. And it turns out there are explicit reconstruction formulas. So let me just concentrate on these two ones. For a vector field, there's IF, its lateral ray transform. This P coordinate, I should probably draw attention to that in 2 dimensions there's a neat way to parameterize. If you have a unit vector xi, the normal distance from the origin P is a neat way to parameterize rays and write down any kind of X-ray transform or ray transform.
But all these are some variations of radon transforms, yes?
Yeah.
Essentially. So,
X-ray transforms.
So this is a natural parameterization, and also all these formulae, I mean the inverse
Exactly.
is elementary in some sense.
We have to use those elementary formula. Exactly. It has to come down to that. So there's sort of, in a way, there's nothing new. It's just more complicated.
Yeah,
So here we have the derivative with respect to P back projected, and then you take the Fourier transform and then you multiply by frequency. So this is actually a familiar operations in inverting two-dimensional radon transforms. But it turns out that what this gives you is not the Fourier transform of f because it's a vector, but it gives you the dot product with the frequency, which if you put that back in terms of ordinary variables instead of Fourier transforms, that gives you the curl of the vector field. So you can only expect to find it up to a gradient. So an algebraic condition in Fourier space is a differential condition in real space. So in the Fourier transform variable, we get part of f. And for tensor fields, it's something similar, just the same operations, a back projection operator and a frequency power of frequency. So f is the Fourier transform, b is the back projection operator, which is just the formal adjoint of the 2D radon transform. So it's for each ray incident on the point, you average over that point, which I've written down here. But I mean, so xi of theta is a unit vector in the direction theta. Xi perp is its perpendicular vector. And what it means to back project a function is to average over all the rays that go through that point. That's all it is. It's easier to say in words. Well, we can p is simply that parameter that I said there. Okay, so you can see this is all familiar for people who are used to dealing with X-ray transforms, but you know there's some aspect of it that's baffling otherwise. Okay, so now we put these ingredients together. Let's define lambda and mu to be basically operations involving the data we know. K1 and K2 are the data that we know. K1 we differentiate then back project. K2 we just back project. We take the Fourier transform to y. I don't know why that f's not curly. Should be. Curly f should be Fourier transform. And then we multiply by some algebraic thing involving y, and that gives us some modified form of data. It's a form of back projected and filtered data, lambda and mu, for each plane eta. And so if we regard this actually just as data, then f hat satisfies some algebraic equations in lambda mu. And it's these algebraic equations we have to solve for 3 or 6 planes. Okay. So you need to remember there are 2 data for each ray. The direct data is K1 and K2, and then once we've back projected and filtered it, we called it lambda and mu. Okay, so in a simple case, if we take an orthogonal basis and just for abbreviate lambda and eta I and mu eta I, like lambda I and, oh, it should be mu I, sorry. We obtain some algebraic equations, and now it's sort of, at this point, easy to see it's something we could solve. So lambda 1, lambda 2, lambda 3, mu 1, mu 2, mu 3 are known, and the Fourier transform of the components of f satisfy these equations. You'll see they're actually differential equations. You know, these are first derivatives, these are second derivatives. So we actually have to invert some big system. If it was a nice elliptic system at this point, we'd be home and laughing. So notice that the off-diagonal terms are slightly easier to get, and then the diagonal terms get mixed up in here. There's diagonal terms mixed up with off-diagonal. And that's the crux of it. And the point is that off coordinate planes, it turns out that this system of, well, it's 6 equations for 6 unknowns, but you actually only want 5 unknowns because I've knocked out the trace, and it turns out there are only 5 independent equations here. But I don't expect you to do that in your head. It took us a while to work that out. Okay, so theorem, a trace-free tensor field is uniquely determined by the data on 3 planes for a generic choice of 3 vectors. Not, of course, they just got to be independent. Well, actually, I suppose their outer products have to span symmetric tensors. So in particular, an orthogonal basis will do. The reconstruction algorithm is unstable. You can see that it would be. You have to divide by y's, right? So some small y's will be unstable. So in particular, it's unstable on the coordinate axes where any of the y's are 0. So it's not clear how much that matters. For 6 axes, let us take an explicit choice of 6 vectors whose outer product spans symmetric tensor fields. And it should be possible to make a stable reconstruction. So it turns out that to get the off-diagonal terms, you have to solve this system, which just has a mu's in. And this is non-degenerate only at, it's non-degenerate at any non-zero y. So in fact, it's an elliptic system. You can actually explicitly calculate a determinant. So this one is solvable for any non-zero y, and there's a stability estimate that the off-diagonal terms can be estimated in a 1 over y. So this is inverting a Laplacian, right? Times the mu. So that gives you the off-diagonal elements, and then you have to solve something else for the diagonal elements, which is a bit more complicated. It involves the lambdas and the off-diagonals you've already found. Okay, so we have an explicit reconstruction, and it has a stability estimate which you can summarize as constants involving lambda and mu, but with different powers of y in front of them. Okay, so 6 vectors that we've just defined uniquely and stably determine f with an explicit reconstruction. So we're done. At this point, we can go back to the lab, take some data and invert it. 2 other little points, that one axis is certainly not enough. It's kind of counting. You've got 2 equations per ray. You expect to be able to find 2 functions, and you're looking for 5. There should be 3 arbitrary on a rough count. These are the equations that we have, and so if we only have one eta, we want to get these lambda and mu to be 0 by choosing these. And it turns out, let me just say it very briefly, so that I have time for the other results, that if you choose an orthogonal frame, well, let's say the projection p eta of y is not 0, because otherwise you're done. If it's not 0, we can divide by it, so we get a normalized vector in the p to y direction, and this is just the perpendicular vector to the other 2. So you have this orthogonal frame, and then it turns out that there's a nice trick. To make these equations 0, we just have to, in this orthogonal frame, choose functions alpha, beta, and gamma of eta and y, so that the tensor looks like this. Notice it's trace-free and symmetric. That does it for that particular y, but all you need to do to make an element of the null space is rotate it back to the original frame and then take the inverse Fourier transform. So this constructs an element of the null space. Actually, you can ask whether it's an interesting element of the null space, whether it's anything you'd actually get in real life. Maybe it doesn't matter. And then we could just do one rotation and our life would be easier. These operations are all analytic, and we can choose alpha and beta and gamma arbitrarily. So we can choose them analytic and with the correct decay to satisfy Paley-Wiener, so their Fourier transform has compact support. And of course, in real life, we're doing it an object with compact support. So it is enough to worry us. There is a null space of something with compact support that you can construct in this way. I don't know if that's a whole null space, but it's certainly one way of making a null vector. Okay, so I'm going to say a few words about stability, and then I'm going to show you some numerics. So first of all, I just wanted to say a little bit about doing the Radon transform slice by slice, because it's kind of interesting. We usually think of the 2D Radon transform on one plane at a time, or the 3D X-ray transform, which can be any ray. But in practice, you quite often take slices for each value of z, and so actually inverting the slice by slice Radon transform. So we just need some estimates for that. In fact, actually, I only need the back projection operator, but it's just interesting to draw attention to this. So R bar is the 2D Radon transform done on each plane for a fixed z. So theta and p are the variables that denote one ray in the plane of a fixed z. And we, on an ordinary function in the Schwarz space, we just fix z and take the Radon transform. You can extend this to distributions using the slice back projection operator, which is just back project for fixed z, and then you can determine its action on the test function just by applying the adjoint. So it has a well-defined meaning on S dashed. and so one can attempt to define subleft spaces of these things and stability estimates. We're going to use a fairly natural norm on the data of slice-by-slice radon transform, which is defined here. And it's quite clear that R bar is bounded on a big enough subleft space, a high enough subleft space, because the radon transform on a plane is bounded in the right subleft spaces, and we also have the trace theorem if we have S high enough. So you can actually just restrict to a plane if S is high enough. The interesting thing is it should work without invoking the trace theorem. So it's probably defined for other subleft spaces. But actually, we're only interested in the inverse of this. And so there's an estimate of F in terms of a subleft norm of the slice-by-slice back projection operator. And of course, this R bar is the slice-by-slice filtered back projection operator. And that's what we're going to use in our inversion, a slice-by-slice back projection, filtered back projection operator. So that's why I told you about this. One other little thing that is just worth noting, that the Hilbert transform, which is take the Fourier transform and multiply by I times the sine of frequency, on one variable at least, is a subleft isometry because it doesn't affect the Fourier transform, the absolute value of the Fourier transform. And so my K1, I'm going to take the Hilbert transform of it and denote that by a bar. And then in that case, all I have to do to get lambda is R bar inverse, that's the filtered, that's the slice-by-slice filtered back projection operator, which we know an estimate for, times K1 bar, the Hilbert transform of the K1 data. And then it's quite easy to say that the inverse Fourier transform of lambda, which we call data, is estimated in terms of the this subleft norm. And we have something very similar for mu. Now, I suppose I want to explain what the consequence of not having data at small frequency is. Even if the argument was quite complicated, the idea, those systems of equations that have powers of lambda times Fourier transforms of the thing you want, simply have a problem when you try to divide by the frequency 0. And you'd have the same problem if you just did a naive Fourier transform for any PDE and then inverted it, you know. So it's a familiar problem. And the thing that helps us here is that we're only interested in compactly supported functions. So, of course, low frequencies are irrelevant for compactly supported functions. Right? And so what you can do is, if you just define what engineers will call a high-pass filtered version of Fij, which sets the Fourier components to be 0 outside some epsilon neighbourhood of the origin, then certainly with the estimates that we have, the Fourier transform high-pass filtered can be estimated in terms of our data in a stable way in subleft norms for any S, actually. And we have explicit bounds for this. So the only question that remains for the theory is does that matter? Well, of course not, because as soon as you've got a function whose support is in the ball of radius A, then the high-pass filtered version of it stably and completely determines F for any epsilon less than half the diameter of the ball. It's kind of an elementary, obvious fact. Okay, so finally, to go to numerics. So we didn't solve the nonlinear forward problem. We didn't solve Maxwell's equations. We assumed that the linear approximation was valid. I suppose I should say some words about it. We did wonder how valid it was. And the two steps in it, first of all, is it quasi-isotropic? We got a laser beam, such as this, put it through our sample, if you see one spot on the wall, then you have ray propagation. If you put something very anisotropic, you'd maybe see two spots on the wall. Certainly a calcite crystal would do that. So we see no divergence, no separate rays. We only see a change in polarization state. So the ray approximation is valid. The linearity approximation for Riertoff's law is not quite valid. We have to work very hard. We have to put a small enough stress that it's valid, but large enough that we can see it. So there's a sweet spot for that, actually. That's quite a real difficulty. And it actually would be sensible to do the non-linear, the Riertoff version of this problem. It would be more useful experimentally. So we chose F arbitrarily and not related to photoelasticity. In other words, we didn't solve any elastic equations and deduce an F from it, which we could have done. F has compact support. Of course, we have to, because it's computer. We have that many voxels, and that a camera with that many pixels, so quite a low resolution camera. And we rotated the apparatus virtually at 1 degree steps. We downsampled the images just to make it a small enough system to solve. And then we added some Gaussian noise. So in some way we've interfered with the data to avoid the inverse crime, really.
Why did you add the... I mean, your data probably was already noisy. Why did you...
No, sorry, this simulated data. We simulated it on this grid, and then we added the noise. Yeah. And then we reconstructed on a smaller grid. So this is... well, of course, I should probably say, you can see that the algorithm really just involves some filtered back projection operators and some Fourier transforms. The filtered back projection operators were the same ones that we used in our X-ray CT reconstruction. And the mechanism of that is you need to know the incidence of rays on pixels. So you have to have some approximation to whether what the integral of a ray intersecting a pixel is. So that's the mechanism we have. And then, of course, we use the fast discrete Fourier transform to do the Fourier transform part. So that's...
And you still use the same filter? Do you use any filter on your...
Of course, we also roll off the filters for high frequencies. Yeah, just as we would if we were doing filtered back projection.
Okay.
But,
so the usual thing plus the usual filter?
Yeah, that's right, but just more complicated. Yeah, the usual story. And so this is our test case. Actually, it looks better on the screen here, I'm afraid. The colours look different, but we have various objects, but they don't appear in all components. That's all that really matters. We reconstructed with only 3 axes, and you can see some artifacts. It actually looks better on the screen.
I'm sorry, I don't understand. What are we trying to reconstruct?
Okay, so this is our original. This is
Which
our
one?
F. Well, it's got 6 components.
Okay.
Right?
So this is what we're trying to reconstruct?
Yeah, this
Very
is our
good.
6
Thank
components. So F11, F12,
Very
F13.
good. Very good.
Okay, and so that's how it should look. And with 3 axes, which remember 3 axes was meant to be
I
unstable,
understand, yes.
we certainly get some artifacts that you can see. I'm not sure that we can understand those artifacts, but
It still looks good.
yeah, it works to an extent, doesn't it? In fact, it works enough to have a reasonable try at doing it experimentally with 3 axes. And then with 6 axes, well, it actually maybe doesn't look so much better. It is better when you look at the error norms, and I think that the point is that the artifacts are slightly less structured than they are. I mean, there are various trade-offs to do. I'm not sure that it's fair to do the same amount of noise for both the reconstructions, because it would take you at least twice as long to do 6 axes. So, you know, you could do the 3 axes and average twice as long and reduce the error by, you know. So I'm not sure exactly what's a fair test in that respect. So I've more or less finished. I have the references here. David Shotton thesis is available online, where the numerics and the stability. This was the paper with Shafutinov, and there's a preprint there in which we did the reconstruction just by treating it as a matrix. And then finally, you're probably wondering whether I've got this experiment to work. Well, I'm very much an amateur physicist, but it's fun to play in an optics lab. And they gave me an optics bench to play with and Tomlinson's equipment. It turns out that making light go in straight lines is much harder than I thought from high school physics. I've learnt a lot about aspheric lenses and spatial filters in doing that. We have actually, well, David Shotton has implemented the code in a way that it takes the data from the automatic measurement system and feeds it into his algorithm. The only problem left to solve is actually my matching fluid doesn't work. So I told you that I had a fluid-filled tank. And let me just show you that. And you might be slightly worried that it was yellow. It's a mixture of liquid paraffin and bromonaphthalene, which I mixed together to make the same refractive index. And you can't see the object in there because it's the same refractive index. You can only see it with polarized light. What I found is that it doesn't stay mixed very well. So we get a variable refractive index in the tank. And so even now that I've got my light to go through straight lines there, and also an afocal camera so it goes straight into the camera, I've got too much error caused by the matching fluid. So matching fluid. It's a similar idea that's used in microscopy for matching lenses. So actually everything is solved except some physical chemistry. I need to mix some better matching fluid and then I'll be able to try it on experimental data. Okay, that's all. Thank you very much for your attention.
Any questions?
Yes, so a little bit after this picture, you say that you can use a ray approximation provided that the index and the derivative of the index stay nice.
Yeah.
This is why you put a matching fluid there.
Okay, slightly different. If the matching fluid wasn't perfect, then the ray would deviate from its path as it entered the object and then would deviate again on the other side. And I would have to calculate that ray path. It would be possible to calculate it if it was known, but it's just, and in fact for a cube, that would be easy. The difficulty is if I put a nut and bolt or something complicated machine component in there, then I would need to calculate the refraction at the surfaces.
You don't see that's what it's part of, because you also have a glass here. So you don't
Yeah,
see part
so
of it is messing up your...
Right, so the ray is incident normally on the glass, so it goes straight through. Okay, so I don't need to match that. Then it goes to the matching fluid, and then it's incident on the object, not normally. So it would generally be refracted. But if the object was unstressed and I had my matching fluid correct, it will go straight through. But then only the polarization component will vary. And in fact, at the moment the problem is actually the refractive index isn't even uniform. It's not even mixing that well. So it's part of the mixing curve of the two components that I use isn't working very well. I mean, you also might notice that it does attenuate light, but the measurements we make are relative intensities between the polarizers. So that actually cancels out, and that doesn't really matter.
Questions?
Yeah, I thank you very much for this very interesting talk, and we look forward to the real experiments. I have maybe two, three quick questions. One is, when you did these numerical experiments, when you invert, then you can take as many angles as you want to improve your reconstruction. But in practice, I would like to know what limitations to have. That's one question. The second question is, when you mentioned that the linear approximation is not very good, if one tries to do the nonlinear problem, what does it involve? And the third question is, can you think of any problem where instead of having the radon transform, you have the attenuated radon transform? Is there any problem that this can come in?
Okay.
Thank you.
Right. the first question is what limitations there are on the rotation. Actually, it's one of those trade-offs of time against accuracy. When I measure the polarized light, I rotate the polarizer and the analyzer with a stepper motor for each picture that I take. So each pixel and each rotation stage, I could take 8 or 16 measurements, and I could also sit there averaging to get rid of noise. And then, of course, then I rotate the apparatus through 1 degree or 2 degrees or so on. So if I want to finish the same day, then I have a choice about how many angles. I mean, in practice, it takes about a day to do 6. I mean, it's sort of order an hour or so to do 2 degree steps, something like that.
But in principle, therefore, you have freedom if you have enough time to do as many.
Yes.
So that's not the problem. Okay, thank you.
Yes. Yes. So it's actually just trade-offs in accuracy. And in fact, another thing that's perhaps not so obvious, that when you move it, you get flow by refringence in the matching fluid, and so you either have to average over that or let it settle. So
to wait more.
yeah. So there's a reason not to go too fast in the rotations. So right, that was the first question. The second question, I can't remember.
Non-linearity.
Non-linearity, right. So in principle, what to do is fairly simple. We just use Newton's method, right? The linearization of the Ryatov law is this. Well, actually, Newton Kantarovich, keep the same derivative and just solve the forward problem nonlinear with an ODE solver long ways. So that seems possible. We just thought we'd get this to work first. And if you want to understand the problem, it's that when you load something, there's a very high stress intensity near the point where you load it. And of course, it's an elliptic problem, so it smooths out very rapidly. And so if you're interested in the highest stress, you're not going to measure the lowest ones that accurately. But if you want the highest stress to be in the linear regime, then you have to be very careful not to load too much. So I think we need to do the nonlinear problem. And then the third one is an emission computed equivalent of this. So if you had light sources within a birefringent medium, it depends if you wanted to find the light sources. One of the classic problems in birefringent media is a layered atmosphere. So where the atmosphere has different layers which homogenize to an anisotropic medium. You can imagine that there might be radio sources and the same equations on a different scale. Yeah, so I imagine there would be emission computed tomography, things in that. Okay.
Seems not. So let's thank the speaker again.